In this lesson, we're going to talk about types of polygons and names that are given to them and how we can calculate the number of degrees that are in different polygons. We use the word convex to mean any two points in the interior of a polygon would have the segment joining them remain totally in the interior. For example, if I draw a polygon that looks like this, no matter where I position 2 points in that polygon, the segment that joins those 2 points would remain in the interior of the polygon. A non-convex, sometimes we use the word concave, is a polygon that if we position 2 points and we join those 2 points with a segment, a portion of that segment is outside of the polygon. So this is concave because I have 2 points where a portion of the segment is in the exterior of the polygon, and I have convex where no matter where I position 2 points, the segment will always be in the interior. So this is considered the interior of the polygon, and this is considered the exterior of the polygon. Concave, or some books call it non-convex. I like to use concave because cave means caved in, and that helps me to remember that this shape is different than this shape. Now, in our study of geometry, we almost always speak of convex polygons, and we give names and we learn properties that all deal with convex. This is an example of regular polygons. And remember that when we use the word regular, we have 2 meanings. First, we say that all sides are equal and all angles are equal. So this is a regular triangle, which is equilateral and equiangular. This is the regular quadrilateral, which is the square, the regular pentagon, the regular hexagon, the regular heptagon, and so on. You can see that the more shapes that we end up with, or the more sides we end up with, the more circular that the polygon becomes. We learned in an activity in our previous lessons that a triangle has the sum of its 3 angles to be 180 degrees. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180. And remember, when I use measure, I do not use the degree sign. But if I'm talking just about the degrees, this is 70 degrees, this is 60 degrees, then I can use the degree sign. But as an equation, the degrees is not, the degree sign is not used. All right, now I can base this concept to help me determine the total number of degrees in any polygon. So keep this in mind as we begin looking at names of the polygons and how many degrees there might be in the sum of the angles. In your textbook on page 17, you can see the prefixes that go along with the number of sides that a polygon might have. Tri meaning 3, quadra is what we use for the name of a 4-sided shape, quadrilateral. But in your textbook, they use tetra as the prefix for 4. 5 is penta, 6 is hexa, 7 is hepta. We don't talk very much about a heptagon, and it's because that when we try to find the number of degrees, we end up with a fraction for each, if we're talking about a regular heptagon. But there are some shapes that are in a heptagon, and it's interesting if you Google heptagon shapes to find out what kind of shapes are a heptagon. 8 is octa, 9 is nona, 10 is deca, 11 is hen, and a lot of times hen deca is 11. An undagon is what we use for 11 in some books instead of a hendecagon. 12 is dodecagon. 13 is tricaesadecagon. 14 is tetracadecagon. 15 is pentacadecagon. I know in high school geometry, probably when you got past 12, we just used the number of sides that the polygon had and then gone after it. So if we were talking about a 15-sided shape, we did not call it a pencadecagon. We called it a 15gon. So if you had an 18-sided shape, it was an 18gon. So it was much easier to use the number of sides in the word gon than trying to pronounce these words or trying to write them. So you can go ahead and look on page 17 for the other names that are given to the polygons. And we go up to a 20-sided shape, and that is a icosagon. More examples of irregular polygons. This is what a regular dodecagon looks like. And again, notice that the more sides that we have, the more circular that it becomes. This is a regular decagon. Now, we like to talk about regular polygons because we like to find the measure of each vertex angle, because each vertex angle would have the same measure, so it would be easy for us to calculate the measure of each angle. Now, if we wanted to find out the number of degrees in a quadrilateral. Whether it's a square, whether it is a trapezoid or a trapezium, any four-sided quadrilateral, I'm going to make a trapezoid. If I begin at one vertex and I draw all diagonals that I can from that vertex, which would be only one possible, the sides would not be considered a diagonal. So there is only one diagonal from A to C. That divides this quadrilateral into two triangles. And we have established that a triangle is 180 degrees. So if I have two triangles, that means that a quadrilateral would have 360 degrees in the sum of the angles. So if I take the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D, I get 360. And it does not matter the shape quadrilateral that we use, because the diagonal from A to C on the square would still give us two triangles. So we can make the assumption then that a quadrilateral has 360 degrees in the sum of its angles. Now, let's say that we are looking at a regular quadrilateral. So we're looking at the square. If the sum of the angles is 360 and each angle has to be equal, then 4 into 360 would mean that each angle is 90 degrees. Now you are going to do a polygon activity, and in this polygon activity you are going to draw as many diagonals as you can from a single vertex. Count the number of triangles that you have, and then calculate the total degrees in that polygon. Then if it is a regular polygon, which these are, then you can calculate the degrees of each vertex angle. So let me show you what I want you to do. You are going to have a shape. You will calculate the number of triangles that can be made. You will calculate the total degrees, and then you will find the measure of each angle. This is a regular polygon. Alright, so let's say that I give you a hexagon. You begin at one vertex and you draw all possible diagonals from a single vertex. You count the number of triangles that you have. So there would be 4. So 4 times 180 is 720 degrees, would be the sum of the angles of a hexagon. But since it's a regular hexagon with 6 vertex angles, then I'm going to divide 6 into 720, and I will get the measure of each vertex angle to be 120 degrees. Now, there are 3 different types of angles that we are going to be looking at. The angles that are formed by the sides those are called vertex angles. And that's what we've been finding the measure of each vertex angle. If I extend the side at A, I have an angle formed here. And if I extend the side at F, I have an angle. And if I extend the side at E, I continue to do that for every side and vertex. There are 6 angles formed, 1 at each vertex, and those 6 angles are called exterior angles. And the cool thing about those, if you remember about a linear pair of angles, a linear pair of angles are 2 angles that are on a line. Well, they're supplementary. So that means that if I have the vertex angle to be 120, then this angle is going to be 60. The same here. This vertex angle is 120, so this will be 60. Each of these angles will be 60. There are 6 of them that are 60 degrees, which means that the exterior angles are 360 degrees, or the sum. So the sum of the exterior angles is always 360 degrees for every polygon. So if I gave you a heptagon, the sum of the exterior angles is 360. If I gave you an icosagon, the sum of the exterior angles is 360. So my question to you is, let's say that you have a decagon. What would be the measure of each exterior angle? So all you have to do is take 360 and divide it by the number of angles you would have. So in a decagon there would be 10. So 10 into 360 would mean that each angle would be 36 degrees, each exterior angle. So taking 360 divided by the number of sides, or the number of angles, will give you the measure of each exterior angle. So we have vertex angles and we have exterior angles. Now, if you have the hexagon that we are looking at, and you are looking at the center of that hexagon, if you draw a radius to each vertex, you have basically a circle. So we call these angles that are formed here central angles, just like we did when we talked about central angles of a circle. A polygon has central angles, and the sum of the central angles is 360 degrees as well. So if you're dealing with a regular polygon, the central angle will equal the exterior angle. So the central angle and the exterior angle are equal in a regular polygon. So you're going to do an investigation. You can use Geometry Sketchpad to draw your shapes and your diagonals if you like, or you can just draw them on paper or use the paper that I provide. So it's totally up to you, but I want you to fill in the chart with the information that tells the number of degrees in the polygon, the measure of each vertex angle, the measure of each central angle, and the measure of each exterior angle.